Hello again, this is Mark Summers from Summers Technical Services. We're continuing on with our little laminate test specimen. We're doing did some hand calculations earlier. Now we're going to do a little Solidworks simulation. See if we can learn how to extract stress levels and displacements that we're looking for our analysis, and also figure out how to do the just running the simulation in Solidworks. So let's get started. So here's a drawing I've done to quantify my shape of my test specimen. I've got some mechanical properties up here that I extracted, and we'll put those into SolidWorks. The hatched area is the area that we're going to grab onto that thing like we talked about before. And we'll eventually apply orthotropic materials to this thing to see how those work. So let's toggle over here and look at the actual part model. So this is a model I asked you to make. It's based on the standard that you've got from ASTM Compass. And we're going to start off just running a static analysis with a linear isotropic material, and we'll just pick an aluminum alloy just to run it and see if we can match our numbers we got with our hand calculations. So 6061 T6 is kind of my favorite aluminum alloy, so we'll use that. So that's assigned. And I've also, you're going to need to add these two sketches here. The sketch, when I constrain this face here where we're grabbing onto it and our test machine downstairs, I don't want to grab the whole face, I just want to grab these edges here. So I have to be able to split this face here on each side, and to do that I need to have a sketch there. And so I put that sketch in there. You'll want to do the same thing. All right, so let's start the simulation. You'll have to, if you don't see your simulation tab, just right-click on these tabs here and turn it on. Sometimes it's turned off, but mine's turned on. There it is. So we're going to start a new study. There's only one button we can push. So I don't like to use these advisors. They hold your hand and they walk you through it, ask you a bunch of questions, but I generally know what I need to do. So I'm just going to say new study, and I'll call it static aluminum. And we've got lots of different options. We ought to do some videos on these. If you're interested in doing any nonlinear or fatigue or buckling testing, we can follow this up with some of that. That's all included in your simulation package we have here on campus. All right, so I'm pretty much answering questions left to right. Here's the first thing I'm going to do is apply my material. And you'll notice down here at the bottom, I've got a new tab down here. This is my simulation tab. And I can have multiple simulations using the same model, and it's all self-contained in this one part model, which is kind of nice. And I've got a new tree over here. I'm on my static aluminum simulation tab. So I've got my new tree here, and it's going to tell me things like how am I holding it, how am I going to load it, and what kind of results I have. And if I want to go back to the model, I just click the model tab. And now I'm back in my familiar feature manager that you're used to seeing. All right, so go back over here. And it says apply material, so I'd apply material, and what does it say? Decides not to start working. Apply material, here we go. And it already knows in the model, in the part model, it has aluminum 6061 T6, so I want to apply that here as well. Apply and close. And there it is right there on my simulation tab. So what's the next button? Fix your advisor. And so what I want to do is I want to fix the geometry on this side. This is the side we're clamping it and we're holding it and we're not letting go. We're not letting it move in any direction or rotate in any direction. So I'm just going to use the fix geometry button. And I need to split this thing. So I'm going to go to the split tab, and it's going to ask me for a sketch. So I want to grab that sketch, and then I want to say what face. I want to split that face. And I'll say create a split. And sure enough, now it's split into 3 separate faces. And I need to go ahead and do that on the other side too. How do I do it again? Let's get out of there. So there's the split. If I go back to the model, there's a split. So that's a part of the model feature. And so I need to do the same thing on the other side. So let's go back to this guy here. Let's go back to fixtures, fixed geometry, And again, I want to pop over to split. I'm going to select the sketch. I'm going to get this sketch on this side, and that's the face I want to split. Create split, and now I've got them split on both sides. Could have done that in the model, probably should have, but here we are. All right, spacebar, ISO view. All right, so now I can finally go over here and actually do my fixtures. Fix geometry. It's asking for the face to fix. I want to fix that face and that face, and then I say okay. So now that side is fixed. I've got a nice little indicator down here that that's fixed. Now this other side, I need to fix it, but I need to let it be able to move in the Y direction. Look at this tab. Look at this triad down here. The Y direction needs to move. And so I'm going to come over here back to Fixture Advisor, and I want to say Fix Geometry. I want to grab this side, and I want to grab this side. Except I don't want to fix all three directions like I did over here. I want to go down here to Advanced, and I want to use Reference Geometry, and it's asking for what geometry is my reference for direction. I want to make that active, make that a blue box. And I want to choose the top plane because I want to tell it to let it move normal to the top plane. So if I use that for my reference, now I'll come down here and say, how much can it move this way, and this way? Well, this way, I want it to be able to move. That's normal to that plane. So I'm not going to turn this one on. I want to turn these two on. That one and that one. I'm going to say 0 movement, 0 millimeter translation. This way and this way. But normal to that plane right here, I want that to be able to move. So that will be allowed to go up and down, but it won't be allowed to go in the other two directions. So I think I can say OK. And you'll notice I get a little bit different icon. It doesn't have all three arrows like this one over here, so you can tell what we're doing there. All right, now what do I need? Well, I just need to go to the next button. Now I've got fixtures done. I did the material, I did the fixtures, and now I'm going to go to loads, and I can do torques and pressures and gravity and all kinds of loads. I want a force, and if I remember correctly, I had 100 newtons, and so force or torque, I want force, and it's asking me where do you want it to be applied, and I'm going to say I want it here, and I want it here, and it's guessing that I want to push up from the bottom and down from the top, but that's not it. So I need to change my options. I don't want to go normal to the face. I want to go a selected direction. And again, I have to pick a reference geometry to define the selected direction. And again, I want to select the top plane to define the direction as being normal to that plane. And so selected direction, the blue box says, what do you want to use as a reference for direction? I want that guy. And I want to add the force normal to that plane. I want that bottom button again. I want the force to go normal to that plane. So I want to turn it on. And here I have to be careful. I don't want per item. I've got two faces. I want to do a total of 100 newtons. Right? That's what I did on my hand calculations. I had 100 newtons pushing up. And this is normal direction. And you can see the indication. It gives me my purple arrows. And they're both going up. So I get an indication that maybe I did that right. All right, so I'll say OK. Now what? Well, hell, I think I'm done. Connection Advisor, that's for doing assembly models. If you got parts that are in contact, they got friction, they're welded, those kind of things. But since we don't have an assembly, we don't have to worry about that. And now in Shell Manager, if you're doing, if you got 2D surfaces, you can do shells. Now I want to run the study. Before I run the study, I'm going to pull this down and I want to create the mesh. It creates a mesh automatically, but I want to show you. And this is a huge part of the simulation, and I'm going to spend this much time on it because we need a whole new video to talk about doing mesh. But we'll go over the basics here. Create mesh. I got this little slider. I can go coarse, big elements. It's going to solve very fast. It's going to be a really lousy answer. I can slide it all the way over here, and I can say give me a fine mesh, which is going to be small tetrahedrons. Assume you know about tetrahedrons. That's the shape of this mesh element. We need to do a whole nother video on that stuff. So anyway, take my word for it. Fine mesh is going to be small elements, longer computation times, but better answers. So normally what I do is leave it in the middle. I can reset it to the middle and let it do a nominal. And there's all kinds of other options. We'll just take the default. and I'll say OK, and I'll take a look at the mesh. Hopefully it'll display the mesh for me when it computes it. So let's go here. OK. Here we go. Computing the mesh, and boom. And so I'm not too happy. This has only got, you know, one element to it. There's only one element width across here. Normally you want to have at least 3 elements across there. So I don't like that. So I'm going to go back up here and say create mesh again. And I've got me a high dollar computer. I'm going to slide that all the way over and then see what it does. Okay, that looks like the bare minimum. 3 elements across there. So, all right, I'm happy. I'll leave that. I've got other options. I need to probably try more mesh. Get an answer, run it again with double the mesh, and if the answer doesn't change, then I know I'm good. All right, so that's it. Now I'm going to save this thing in case something crashes. And so you save this thing off. And so now I'm ready. The next button is just run this study. So let's see what happens. So when this thing is running, it's computing the, sharing violation occurred. What the heck? So let's save and close and try again. Do I have 2 sessions of Solidworks going? I hope not. Maybe I got it open twice. Maybe I got to have the drawing closed. All right, let's try this again. If this doesn't work, then maybe we'll give up. No, not really. All right, is that what I want? I saved it. It should still have all my mesh. I'm going to bump over here to my static analysis tab and see that if I do my mesh, looks like it's still there. That was weird. I don't know what happened. All right, so I'm back where I was. Let's run it again. Maybe I don't have the fastest computer. Okay, that's telling me I need to run it. Okay, so I'm going to save. Now we're going to come up here and push run this study. And see what happens. Here we go. Now we're rocking. I'm going to hit more. So it tells me I got 250,000 degrees of freedom, about 80,000 nodes, 50,000 elements. And so, man, that solved it fast. All right, now what do I do? Well, it gives you results, and it's not going to give you what you want. It's going to give you these defaults. It gives you von Mises stress, which you'll learn about if you take my machine design class. And we talk about it in mechanics and materials too at the end. So we don't want that. Here's displacement, here's strain. What I want is the shear stress in the middle here. And we got to go back to our talk the other day. We need to figure out which one we want. So here's the key. Look at this triad down here. I want the shear stress on the face that's going right through the part right here. I want the shear stress on that face. And that shear stress, that face is defined by the normal direction. And what's the normal direction? If I look down here in the corner, the normal direction is X. So I want tau on the X face in the direction of the shear force, which is up and down. So I want tau X, Y. That's what I want to ask for. So I'm coming up here and I'm going to right click on results, define stress plot, and I want tau, what did I say, XY? Von Mises stress? No, I want tau XY, there it is. And you might say, well, wait a minute, Summers, you told me there were 6 shear stresses and 3 normal stresses. Where's the other 3 shear stresses? Well, remember we talked, there's equilibrium on that stress element, and those shear stresses cancel each other out. So tau XY is equal to, by definition, tau YZ. Similarly, tau XZ is equal to tau ZX. And YZ is equal to ZY. So they don't put all 6 of them up there, just going to take up space. So, but know that that symmetry happens and you can get the one you want. So we want tau XY, and I want my units to be in megapascals. I don't want newtons per square meter. I want megapascals, so I'm going to change the units there, and I'm going to say OK. So this is interesting. So it gives me this deformed plot. See the deformed result button? It looks like it's deflecting, you know, gigantic amount, but this is way over exaggerated. What's the deformation scale is like 7,000. So it's not going to deform that much. That confuses me, so I'll usually turn that off. So it goes back to static. So here we go. Right here in the middle, we've got, this is where we want to calculate our shear stress. And there's a little bit of a higher shear stress here at the near the top, I suspect due to that maybe a stress concentration due to this guy, but it's really growing anyway because of our CAN calculations we did. Remember, it's a VQ over IT, and it's going to vary as we go up and down, but this must be due to the stress concentration. So anyway, I want to look in that face and find out what my shear tau xy is, and I can do that using this plot tool. And so if I select the plane I want, which is going right through the middle, I strategically located my part planes right through the middle of the part, and now all my hard work is paying off. I want to look at the stress right there. So I'm going to select that, go to plot tools, and say section clipping, and now I'm on that face, and I'll say okay. Now I can spin it around and look in here, and I can look at the color, and I can try to find where I'm at over here. But I've also got this plot tool probe, and I can click on this face and get multiple values at multiple locations just by clicking on it. And since this is the active stress is my shear in the XY plane, it's going to give me those values. And so what are these values? Well, it says 9 e to the minus 1, so that's 0.9, 0.87, 0.87. So this is making sense to me. Why is it making sense? Because the stress is slowly getting greater as I get closer to this stress concentration. But look at the values. They're all about the same. They're all about 0.9 megapascals, which was very close to that average stress that we calculated. We calculated, what was it, 0.94? And so this is correlating well with our analysis we did. And so I think I believe these values. All right, so that's doing the probe. We can also ask for a displacement to see if this thing is making sense. I want to look at displacement in the Y direction because that's the only direction it's really moving. So I'm going to click on results again. I want to right click on it and ask for another plot. Instead of a stress plot, I want a displacement plot. And I want to ask for displacement in the Y direction, U sub Y in millimeters. And does this make sense? Well, here's 2e to the minus 8, so this is 0. And that makes sense. This is the side that I'm clamping. I'm not letting it move. And then it just goes up just a tiny fraction of a millimeter over here, but it is going up. That's a positive number. So that makes sense. It's going up over here, and it ends up going to 0 over here. So I think, again, I believe these values. So when we look at the analysis we do with the other material, we'll compare those values. All right, so I don't know. Let's keep going. It's kind of fun. So now let's go start a new study. And I'll come up here and say new study. And I don't know. I'll call this static composite. Come on. There we go. And you'll notice I get another tab down here. And I probably should have, there's a way to clone these things. Let's see if I can do that. If I right click up here, copy study maybe, let's copy study. And I'll say, I'm going to copy that one. I want to call it static. I think I misspelled the other one. CMPOSITE. All right, so I'm going to clone. That way I don't have to redo the constraints and the load and all that stuff. And so I'll just have to change the material, and I think that's it. So there's what I got here. This guy I'm just going to right-click and delete. And again, all of these stay with the model, and so this is really handy. There's the aluminum one. I'm not going to touch that one. Here's the new static composite. All the constraints are the same. The loads are the same. I need to change the material. So I'm going to come over here on my 6061 and edit the material. right-click and edit material, and I've just so happened that I created a custom material. I hope it's still here. There it is. I called it my friend Harish that is my expert PhD guy that's helping me out with all this stuff. So these values came from Dr. Tate's lab, this material. And this is what we talked about the other day when we got linear elastic isotropic. We've got one value for elastic modulus, one value for Poisson ratio, one value for shear modulus. But we don't have linear elastic isotropic material. We have linear elastic orthotropic material. Now I've got my three values for Young's modulus, three values for Poisson ratio, and three values for shear modulus. And these values came right off the drawing. You can create your own material. So the last thing we have to do is we have to add this reference geometry. The reference geometry is going to tell us which way X and Y and Z are, as we defined the other day with our first video. So if you didn't watch that, you're screwed. Go back and watch that video and come back. X, Y, and Z, I want to define that, and it's asking me which way is the X direction and which way is the Y direction. And it turns out my front plane is on the XY plane, and so if I select that box for reference geometry and select my front plane, that will, and apply and close, that will define which way is Young's modulus in the X direction, Y direction, and Z direction. So now my material is defined. I get a warning on my results. It copied the results over from the other model, but that was with the other material, so it's giving me a warning, say, hey, you need to rerun this thing. So let's go to the mesh. Let's create the mesh. And I don't know, 3 across there was nice. Let's see if we can do, I don't know what I'm doing here. Mesh parameters. Oh, here we go. These are some mesh parameters. Let's play around with this number here. Let's make this half as big. So I'm going to take that number and divide by 2. These get created with this slider. And I can't slide more than all the way over to here. But I can change these numbers here. So I'll have this one. And we'll say OK. And then we'll see what happens. So they should double up or half the size of the mesh instead of having, well, let's see what it does. It probably will have twice as many across there. I guess it'll quadruple the number of elements because it's an area, it's a volume thing. So let's see. I can't remember what the number of elements were. Should have wrote those down. So yeah, there we go. That looks much better. So now I've got, instead of 3, I got 1, 2, 3, 4, 5, 6 across here. So I have that. That makes sense. I have the distance in all 3 directions. So I've got twice as many elements across here. I got twice as many elements going the other way. So I guess it's 2 to the 3rd. There's 8 times more elements. So this might crash and burn here on my computer, but what the heck, we'll give it a shot. I want to save this thing, and then I'm going to run this study. And this is going to take a little longer, so that'll be actually a good thing because I want to show you some of these parameters as it's computing. It's kind of fun to watch how it's converging on the answer. And so it's creating this ginormous stiffness matrix, and it's having to invert the compliance matrix we talked about before. Remember, we had a compliance matrix? Go watch that video if you missed it. It's got a lot of good stuff in there. Probably more than half of it's actually good, true. But anyway, they've got the compliance matrix, and then we do an inversion. We invert that gigantic matrix, and we get the stiffness matrix, and that's what it uses here. So it's got to invert these huge matrices, and they're thousands and thousands of elements. So let's go more, and right now it's solving. So, my Lord, I've got, instead of having tens of thousands of degrees of freedom, I got over 1.5 million degrees of freedom. Number of nodes, that's the number of corners. Those tetrahedrons are triangular shaped faces. 3 triangular faces make a tetrahedron. So there's 500,000 nodes. There's 400,000 elements. And it's crunching along. If I click on this convergence plot, it might be too late. No, it's got a ways to go still. So the convergence plot gives me an idea of how it's converging on the correct solution. And so, again, we need another video to talk about these, but it's got different ways to tweak the mesh and or tweak the polynomial equations that define how the displacements and strains change between those nodes. And you can have first order polynomials, second order polynomials. In areas that have large gradients of stress, it will automatically, depending on if you're using a P method or I forgot the other method it uses, whether it changes that polynomial or changes the size of the elements. But anyway, we need more videos here. So we'll talk about that another day. So here we go. Looks like it got running. It got converged on an answer. And there it is. And so it remembered my stresses that I asked for before. And so let's go look at them. So here I'm gonna activate this stress, this shear in the XY. This is tau XY. So I'm going to show that. Right-click Show. And I'm going to go, and it's already remembered my cut section clipping. And now I'm going to go back to Probe, and I'm going to probe this thing and see if it's different than it was on my aluminum part. And it looks exactly the same. So what do you think? How can the stress be the same for the aluminum as it is for this guy? Well, think about it. What parameters were in our equations we used? We had areas, we had moments of inertia, we had first area moment of inertia, we had forces. Did you see Young's modulus in any of those equations? Did you see shear modulus? For stresses, it doesn't matter. Stresses are stresses. Doesn't matter what material you have. Now, the stiffness is different. And when we do displacements, we're going to get different values. Because if you do look at those displacement equations, they have Young's modulus in there. They've got shear modulus. It takes into account for displacement. But for stresses, these numbers are exactly the same. So that's good. And if we want to look at displacements, I'm going to right-click, show this one. And so I don't remember those other numbers, but these should be different values than we had before because it's got different stiffness parameters. And so, anyway, that's a first pass at being able to do SolidWorks simulation and setting up isotropic materials like aluminums and steels like we're used to using in most of our engineering classes. But with orthotropic materials, you have those different parameters for different directions because this is a laminate. Go look at that drawing. If you didn't get a copy of that drawing, send me an email. It's got different strength properties depending on which way you're pulling on it. This is a laminate going this way and this way. So these properties going side to side and going in both directions, X and Y are the same, but going this way is different. And if we use this material in a loading condition that's got out of plane loading, then those stiffnesses will come into play. So that's it for now. If you've got some suggestions for additional videos, send me an email. I'll put my email up there so you can get a hold of me. You should have already, if you watch those other videos, hopefully you've already sent me an email and asked for the information for the test specimen. I told you how to get the ASTM spec. So yeah, give me some suggestions for new videos, and we'll do one more using ANSYS Workbench, and it's the same but different. It's the same kind of information we'll be feeding in, and we'll just be pushing different buttons to put that information in the modeler. So until that time, enjoy the rest of the day. And again, this is Mark Summers from Summers Technical Services wishing you a good day.